Hello everyone again. It's my pleasure to introduce our speaker today, Mareike Dressler from the University of New South Wales. Today she is going to talk about Signomial optimization. Yes. It's just start now.
Yeah, thank you, Min, and thanks to all the organizers for having me here. It's actually the first seminar I give in Australia, so to say, so it's really nice. Yeah, so usually I'm more doing polynomial optimization, but I thought for the audience, it's maybe more interesting to take a slightly more general point of view, namely the point of view of Zignomial optimization. So what I'm doing specifically also can be viewed from this a slightly more general point of view. And I hope it will be clear how these Zignomials somewhat generalize this common polynomial optimization point of view. So what I'm going to tell you today about is a very recent work joined with Riley Murray, and we tried to give the common Zignomial optimization a slightly more algebraic perspective. So since the audience is, I think, rather diverse, let me start with a very general overview. So yeah, what I'm going to consider today is Zignomial programming, and first of all, what is a Zignomial? So Zignomials are functions of this form. So they are weighted linear combinations of exponentials of linear functions. So the coefficients are real and also the exponents are real. And Zignomial programming is then just given a Zignomial and some Zignomial constraints. I want to minimize this Zignomial subject to this constraint, or to this constraint set, whatever I have, or maybe also globally. And usually I will denote this optimal value with fk star. And clearly this is a non-convex optimization problem having lots of applications. For instance, in chemical engineering, we will see later also an application in aircraft design, in chemical reactor design. And then we have applications in aircraft design, in structural engineering, transportation systems, communications networks, etc. And the approach to this Zignomial programming is now not via the typical, maybe for you familiar, non-linear approach. Namely, it comes more from this polynomial optimization point of view. Namely, we say, or we note first that equivalent to minimizing such a Zignomial to a constraint set, it is equivalent to finding the largest real number gamma, such that f minus gamma is non-negative for all x and k. So to say I search for the largest shift I can take to this Zignomial such that this function is non-negative. So what I'm really going to focus on is more the algebraic question behind this problem, namely, if a function, in this case a Zignomial, is non-negative on a certain set k, or if I don't have any constraints, if this Zignomial is globally non-negative. And this is actually a key problem in real algebraic geometry. So for instance, for polynomials, it dates back to the 19th century with certain questions of David Hilbert and his 17th problem. Yeah, but unfortunately, this problem is NP-hard in general. since you can cast the well-known positivity problem as such a problem. And the idea now, how one approaches this more algebraic question, is to find inner and outer approximations of cones of Zignomials that are non-negativity on K. So the Signomial set, which are non-negative on K, this forms a convex cone. And this question, if F is non-negative on K, is NP hard, is equivalent to saying membership in this cone is very hard. So one now finds approximations, outer and inner approximations of this hard to test non-negative cone. And these outer and inner approximations hopefully can be checked more efficiently. So membership in these approximations cones. And then one translates these approximations to hierarchies to really optimize over these cones. And they are usually based on so-called Positivstellensatz. Yeah, and in my talk now, I want to tell you a little bit about how one can find such an approximation, both outer and inner approximations of such non-negativity cone via so-called conditional sage. And this is, so to say, the outline. So in the first part, I will really slowly introduce you to the concept of Zignomial rings. We'll introduce a little bit of notation and what these conditional sage I just mentioned are. Yeah, and then I will introduce our new Positivstellensatz, which respects these Zignomial rings, a new concept we also introduced in this paper. And then how one can really grade Zignomial rings by something we introduced as a degree. And from that, we will see we can get a complete hierarchy of lower bounds that approach the optimal value of our Zignomial programming problem. And I will show you our theory in action, namely on a chemical reactor design problem. And if we come to that, then I will outline the outer approximations. For that, we need a little bit of Zignomial moment theory. With that, we can, like I just said, form outer approximations of this cone, which in turn then leads to upper bounds, which converge to our optimal value. All right, so part one, let me introduce you to the concept of Zignomial rings. So we have this ground set, finite ground set, curly A, and this is our ground set containing the origin. And to every point in our ground set, we associate a so-called monomial basis function. This basis function, namely the exponential function, which takes the usual values. And the Zignomial can then be interpreted as follows. So a Zignomial supported on a set A is then describable as such a linear combination. And just because we need it later, we call Zignomial with only non-negative terms polynomials. Yeah, so recall these coefficients can be real, and if they are all non-negative, then we call the Zignomial polynomial. You can remember that with positive a little bit. And the set of all finite products and real linear combinations of such basis functions is then the Zignomial ring. So to say the Zignomial ring R alpha or RA is the R algebra generated by these basis functions. For modeling reasons, and also in much of the literature, Zignomials are parameterized as generalized polynomials. So they are usually written in this geometric form, where t gets mapped to such a form, and the variables here are these ti. So you can see Zignomials in the Signomial rings as generalized polynomials on the positive orthant, because now the exponents can be arbitrary real numbers. And clearly this is well defined, provided that this variable is positive. Yeah, but note here that the polynomial variables are really implicitly linked. Here I show you an example. So these formal indeterminants are not independent of each other. So for instance, if you have the variables t1 and t2, and they define the exponential of x and exponential of 2x, then this gets mapped to the following variables, namely t2 is equals to t1 squared. And maybe one note of caution here, so these implicit links between the variables can be high degree or even non-algebraic. Yeah. Then we need a little bit more of notation, namely for a finite set A, we define R to the A to define the set of real A tuples indexed by these points alpha. And with this notation, we can somehow identify a Signomial just via its coefficients on the basis functions. So it is sometimes better to just view the Signomial being represented by its coefficient vector. And in what follows, this A, we often understand it as a linear operator that takes these values here. And when thinking of A as a linear operator, we can effectively regard it as a matrix with rows sorted according to the lexicographic order on R to the n. And last piece of notation is the support of a Signomial. This is denoted as sub f, and this is just the smallest set A for which f is in the span of these basis functions where the exponents are in this set A. So I guess your usual understanding of support. All right, so now consider a Signomial, and what we wanted to do is we somehow wanted to tackle the question of Zignomial non-negativity, right? And an easy case is clearly if we have polynomials, so if every coefficient is non-negative, because clearly the exponential function is non-negative, the coefficients are non-negative, so then clearly this Signomial is non-negative in this case. So this is super easy. So let's think about the next easy case, namely we have a Signomial where only one coefficient is negative, or at most one negative term. And this is actually something which was somewhat introduced in 2014 by Chandrasekharan. They looked at these kinds of exponentials and they called these Signomials with at most one negative term AMGM exponential, which comes from the AMGM inequality. It will be very clear one slide ahead, or just for short H function, yeah, AGE H function. So whenever I refer to an H function, I refer to a non-negative Signomial with at most one negative term. And it turns out that using a convex strong duality argument, we can handle this situation of Signomials with at most one negative term also rather well. So let's see this in an example. So here we have a Signomial with one negative term, namely here. These are the exponential, the exponent vectors, and we want to know if this Signomial is non-negative or not. So first of all, we can use this identity and convexity to somehow bound the negative term, right? So we note that the that term here, so the exponent, which has the negative coefficient 2, 2, 2, can be expressed as a convex combination of the other exponents, namely so, and then we can use the convexity of the exponential function to lower bound this sum here. So we have a global lower bound on our convex function, and by appealing to strong duality, this shows that certifying can be accomplished in a computational tractable manner by a specific optimization program. And note here that equivalently to convexity of the exponential function, we can take also the AMGM inequality to show that this Signomial is actually non-negative. So note or recall the AMGM inequality, or actually this is the weighted AMGM inequality, is as follows. You have certain variables, they are positive and specific weights between 0 and 1, all the weights sum up to 1. Then you have this inequality, and you can apply that exactly to get this inequality here, which in turn gives you that the Signomial we initially regarded here is non-negative. That's also somewhat where this name AMGM exponential or H exponential or H function originally comes from. Okay, so now we know how to handle somehow situations of Signomials with at most one negative term. What do I do when I have more negative terms? And then I just try to write this polynomial, the Signomial as a sum of Signomials with at most one negative term. So to say, I try to write this Signomial as a sum of H functions, and such a Signomial is then called SH function. So sum of H functions is just abbreviated then as SH function. So each term in a SH decomposition is globally non-negative via the previous slide, and it is easily seen that the SH functions is or has to be also globally non-negative. So now certain facts about these this concept. So checking whether a Signomial is SH or even H can be done by a relative entropy programming. So this is the optimization problem which detects whether this H function is non-negative and what are relative entropy programs. So these are convex optimization problems, and they involve a certain constraint, namely this constraint here, and this constraint defines as the relative entropy cone. Yeah? So it doesn't matter how exactly it looks like, but I think the main takeaway here is that it is a convex optimization problem. Yeah, but note, however, like for all these approximations, in general, a SH decomposition gives us only a sufficient condition for non-negativity to a Signomial. So if a Signomial is SH, then we know for sure it is non-negative, but clearly there are non-negative Signomials which cannot be written as a Sage function, and here is such a guy. So this f is non-negative. One can see that easily because it can be written as this square, but one can also show that it is not Sage. So this duality argument of Sage also generalizes to constraint problems. That is, if we want to test non-negativity on a certain set. So because before we more talked about global non-negativity, right? And now we want to know or test non-negativity on a specific set. And let's give it first again a name. So we call a Signomial xh if f is non-negative on a certain set x. And again, it has at most one negative coefficient. Like previously, we can now take sums of these guys to get x Sage Signomials, and again, these form also a convex cone supported on a specific set A, which we denote as CXA. And in more detail, this cone contains these coefficient vectors which correspond to such x Sage Signomials. That means such Signomials that can be written as a sum of xh Signomials. And there is one important feature which maybe distinguishes it between, for instance, if you think about sums of squares in the polynomial case, right? So for Sage, we have a certain kind of sparsity preservation. And by that, I mean, if f is supported on a certain set A and has, let's say, k negative coefficients, then f is really x Sage if and only if it is a sum of k x h functions, and each of these functions is supported on A. So I do not need to enlarge my support set to get this decomposition. So we have some kind of a term cancellation free decomposition here. Yeah, so this is the primal x Sage cone, and we can also, like for every cone, take the dual perspective. For that, first let's introduce the smaller cones, which comprise our x Sage cone, namely the xh cones. So I hope this is not an overload of notation here. So these xh cones just contain now the coefficients of the xh Signomials. So that means Signomials which are non-negative and have at most one negative coefficient, namely all coefficients with alpha are non-negative, and the beta one is, so to say, the bad coefficient. This is the negative one, or maybe negative one. And then I can write our x Sage cone as a Minkowski sum of these smaller xh cones. And then clearly the dual x Sage cone via standard rules in conic duality is just the intersection of these duals of the smaller xh cones. So this dagger here will always denote somehow the dual formulation. And what now is this small dual cone? It is written like so. So it's this the closure of this specific set. So just for those who are maybe interested in this, I'm not going further in depth here. Yeah, I think now we have established the machinery to understand the Positivstellensatz for these conditional Sage But first of all, let me maybe reinterpret an earlier sage Positivstellensatz, namely given by Chandrasekaran and Shaw in now this language of Zignomial Rings. Namely, then their Positivstellensatz reads as follows. So suppose we have a support set A, and they are rational exponents. So we have rational support set. Again, the 0 is contained is in the support, and we have some constrained Zignomials that specifically include this kind of Zignomials, and this is because we look at this compact set K, where this is the solution set X, where every constrained Zignomial is non-negative. And because we have explicitly included these kind of constraints, we know that this is really a compact set, right? Because this can be seen as somehow a box constraints, right? So we have some constraints, and then explicitly we have these kind of guys, which really ensure that our set K is compact. And then a Positivstellensatz always says if you have a Signomial, or if you have any kind of function which is positive on a certain set, then you can write this this function in a specific algebraic way. And their Positivstellensatz goes then as follows, namely, if you have f in the Signomial ring positive on this constraint set, then you have this identity. Namely, you can write your Signomial as like so, namely as a sum of products of Rn sage functions lambda and products of the constraints. So here you see you have to take products of the constraints. So in the end, this decomposition will be exponential in the GI, so in the constraints. And note that this does not involve conditional sage. This just involves arbitrary sage, because we have here sage which are non-negative globally on R to the n and not on a constraint set. And we now generalize this whole aspect as follows. So our Positivstellensatz is we have a compact convex set X. Then additionally, we have some constraining Zignomials, really arbitrary. We don't make any assumption on it. And we take we consider then this set K, which is, so to say, the intersection of this compact convex set X and the set formed of these other Zignomials GI. And really note here that this set K does not have to be a convex set. So in fact, in general, it will not be convex, right? And then our Positivstellensatz says that if F is positive on this possibly non-convex set, then we have the following identity, which reads like so. So we have here a multiplier, which gets multiplied to this F. And then I can write F as an X-sage function lambda 0 and such a sum of polynomials and the other Signomials GI. So here are several things to note. Namely, when you compare it to the other Positivstellensatz, so here we have we only invoke the constraining Signomials GI in a linear fashion. So before we had here products of constraints, we only have linear constraints. And these are only polynomials. So these are these very easy Signomials which have all non-negative coefficients. And this is X-sage. And we don't make any assumptions on X, or rather it doesn't have to be semi-algebraic, and we don't make any assumptions on the ground set. So we really have here exponents which can be real and not only rational. And we also have no regularity conditions, which you might have heard of, like something like Archimedeanity or convexity or something like this on K. So this is really the first Positivstellensatz that permits possibly irrational exponents and leverages conditional sage in the presence of non-convex constraints. And there is also one specific nice special case, namely when we don't have any additional constraining Signomials GI here. So when this set capital G, which is just the small GIs, if that is empty, then this collapses to the following nice phrase, namely that if F is positive on this compact convex set X, because K is X in this sense, then we have that this modulizer times F is X sage for a specific large enough natural number R. And we can compare it again to another Positivstellensatz by Wang et al. Namely, they gave shortly before us also a Positivstellensatz, which again, if we somehow interpret it in the language of our Signomials and Zignomial Rings, which reads as follows. So again, suppose that the exponents are rational and that the F has a degree 1, this is very important, then it somehow looks like the Positivstellensatz otherwise reads the same. So F is positive on X, then there exists a natural number such that this time to the R times F is X sage. But really note here that our corollary, which follows directly from our Positivstellensatz, generalizes here rational to possibly irrational. And also there is this slight computational heavy difference, namely that we allow that F has a degree greater than 1. And this may lead to a crucial reduction in the size of the relative entropy programs used when searching for these X-sage decompositions. So to say, this is very important in terms of efficiency in the end. All right, so let me shortly, really shortly outline the proof structure here of the corollary. Namely, what we basically do, we take our Signomial problem, then we map this Signomial problem to a polynomial one. Namely, we represent our polynomial, our Signomial as such a homogeneous polynomial. And then one can say that when F, our Signomial, is strictly greater than 0 on the set X, then this homogeneous polynomial is strictly greater than 0 on this polynomial set capital Y. So to say, we map the Signomial problem to a polynomial one. Then we represent Y by infinitely many but countable homogeneous binomial inequalities. And we also have one nominalization constraint. But the most important thing, what we now can do, namely there is something that is called Dickinson-Pohl Positivstellensatz, which gives us exactly that what we want. So to say, we apply a Positivstellensatz from the real algebraic geometry literature. And then we also need a reduction from a semi-infinite non-negativity problem to a finite one, but this is also nice and given. And then we map back to Signomials. So to say, we come from Signomials, go to polynomials, apply some heavy algebraic geometry machinery there, and then we map back. And this entire analysis is also a finely invariant with this ground set A and also this constraining set X. So one can rather easily extend it to this when one adds non-convex constraints GI. So then one can really get the theorem. Okay, now we have a Positivstellensatz. How can we use this identity given by the Positivstellensatz to somehow get certificates for non-negativity, so that we can in the end use it somehow to really do polynomial and Signomial optimization? So for that, we again need some something, namely we somehow need that that we have to decide the support sets of these polynomials here. So by the sparsity preservation, I told you earlier about, we do not need to explicitly bound the exponents for this Signomial, but there may happen something with the exponents here. So we have to somehow decide the support sets of the polynomials. And so how should we go doing about this? So what we somehow have to consider is that the complexity should take into account our Signomial F, this, so to say, this input Signomial. Then clearly this natural number R, and also clearly the constraining Signomials GI. And the problem here is that Signomials itself do not have a concept of degree. So for polynomials, somehow the complexity is always measured in terms of their degree. So when the degree of a polynomial is somewhat large, then it's hard. But for Signomials, we don't have that from itself. So there, the complexity more comes from the number of terms. And that is why we now artificially impose an A degree to these Signomials, and to just have something like this degree for polynomials. And namely, we do that as follows. So we define something which is called the A degree of a Signomial as the smallest number of possibly non-distinct products of basis functions to express F. And to be a little bit more formal, we define the set AD, and the set AD is just the set of sums of at most D vectors from this ground set A, and then you can say we can express the A degree also as the smallest integer D, such that the support is in this set AD. So this somehow, this AD gives us a sequence of nested sets, right? And yeah, like I said, it's not intrinsic to Signomials. It's really artificially imposed by us. And note that unless this ground set is decided by some external factor, one can always update the ground set by the support of F to having that A degree of F equals to 1. And although the A degree is not intrinsic to Signomials, it exhibits essential properties of coordinate system invariance. So for instance, there is a shift invariance, or also an invariance by multiplying by a non-singular matrix. Yeah, so that are very nice properties here. And with that, we also define the ring RAD. And this is just the set of Zignomials in the Zignomial ring that just have a degree at most D. And one thing to point out here is that Zignomial A degree behaves a little bit different than what one knows maybe for polynomials, because for polynomials, this inequality is always an equality, right? So if you multiply two polynomials, then the degree of this product is the sum of the single polynomials. But for Zignomials, in fact, this can be a strict inequality. And let's take a look at an example here to make abstract things a little bit more visible here. So let's consider the one variable case. And we have this ground set, -1, 0, 1, and 2. And we look at the Zignomial x, 3x. Then the degree, or the A degree of f is 2. And why is that? Now we need really two basis functions to express f. So we need here x1x and x2x, right? The product of these two base functions would give me then x3x, and this shows that the A degree is 2. But then if I multiply any polynomial or any Zignomial in this non-trivial linear subspace to f, then we see that the outcoming Zignomial would be c times e2x, which in fact has A degree 1, because I have e to the 2x in my base set. Or more, I have 2 in my base set, which gives rise to the basis function e to the 2x. So you see that this A degree of the product can be really strictly smaller than the degree of the sum, or even the A degree of only one of these factors, which for instance for polynomials is only the case if here, for instance, g is the 0 polynomial, right? And in view of this example, we have to also introduce something what we call the inverse support. Namely, this is just the support set that satisfies the following. So here we put every exponent of a base function in this support set that multiplied with my outcoming or input Zignomial just gives me an A degree of smaller or equal than D. This is just important later to ensure that the A degrees really do not exceed a certain number. Okay, so let's come really to some optimization. So we want to have a complete hierarchy of lower bounds for this Zignomial programming problem. So we want to compute the infimum of f subject to this set. And based on the previous slides, our idea is to now grade the certificates according to the largest A degree of the input Zignomials. And now we can define such a lower bound as follows. Namely, we call it the A degree D sage bound, and we name it as FKD. And this is just the largest real number gamma such that we have this. This is just the decomposition that is given by us for from the Positivstellensatz. And now we just make sure that the A degrees are as we want them to have, namely maximal D. So our X stage is then in this cone here, where AD was exactly that there are sums of at most D base functions. And here there comes into play this inf sub, what we have here. And this again just ensures that this multiplication here, this polynomials times these GI really has a degree, which is strict or which is less or equal than D. So we can efficiently now compute this number FKD here. And if R would be less than 0 here, then we just set this number to -infinity. And maybe note here one thing. So our Positivstellensatz gave us that these lambda I are polynomials, but to ensure the chance of finding a such a decomposition, one can generalize this a little bit and say, okay, we open up the possibility to have it X-age, not only polynomials, so we allow also non-negative coefficients. We allow negative coefficients here. And this, in fact, gives us then a non-decreasing sequence of lower bounds, and upper bounded is it by the optimal value fk star. So we say then that this hierarchy we provided here is really complete. And every such bound FKD can be computed via small but clearly increasing in size relative entropy programs. Yeah, and this is implemented in the Python package SageOpt. And we now want to look at an example, namely a chemical reactor design problem. So we consider the design of a chemical reactor system as described by Blau and Wilder. So this is exactly this reactor exchanger pump system. And yeah, the goal is here just to find the best design of this chemical reactor system. So we want to design the system to produce something while optimizing some economic criteria, like we want to have the cost to be minimized and the profit to be maximized, for instance. Yeah, and this can be written as this proper Signomial program here. So we have this objective function, and I just really wanted to bear you the constraint functions because they're as ugly as this objective function here, and they have the form 1 minus some polynomial in T. And T here, notice, written as xp. Yeah, so how do we go on solving this guy here? So first of all, since the initial problem is really terribly scaled, so if you look at the objective function, here the coefficients, they span already 12 orders of magnitude. So trying to solve even maybe the lowest level Sage relaxation with Mosaic, it returns an unknown status code. So we scale the variables appropriately. And in the end, we I think the coefficients only span 4 orders of magnitude. Anyhow, so the Sage relaxation after the rescaling can be solved reliably. Then clearly we have to decide on the ring we use, and we decide to work in the naive ring. So to say, we take the ground set to be just the support set of F. So all monomials, monomial exponents in the objective function here, we put in the problem. Then one thing to note is that we have here equality constraints. Clearly, they are not convex, so we only have non-convex constraints. So we can infer valid inequality constraints in X and put these non-convex constraints as being these GI I talked about earlier, right? And then we can apply our hierarchy and compute our lower bounds. So the first lower bound gives us this, and the second lower bound already this. And then we run solution recovery on this FK2, and we obtain a point which gives us the value like so here. And we see that this point is feasible nearly to machine precision. So one can really reasonably conclude that this fx prime is an upper bound to fk star, so our optimal value. And clearly, alternatively, one could now approach this problem through a global solver from the traditional non-linear programming community. So we also did that to just compare how our new version does. So we tried four solvers from the 5 in GAMS. One of us was not available to us, so we tried here Baron, Antigone, Lindo, and Skip. So we enforced a 2-hour time limit, and Skip was not able to return a solution, and also no bound before this time was out in both parameterizations, so in the optimization variable t or also x. And all solvers, all other solvers return the solution with objective value roughly to what we also found. And the other, the times and the lower bounds are noted here. So I would say the overall takeaway, what you should see here is that our conditional sage approach produced the same solution as these solvers, but with a relative entropy program that could be solved in half of the time as the fastest of these methods, namely Lindo here. And also only Lindo was able to certify its solution as globally optimal. And by contrast, if we now look at Lindo, the performance of Sage is really independent of whether we regard the Signomials as Signomials, so as function in X, or as generalized polynomials in T. So it didn't make a difference here. Yeah, and I think I'm already out of time, so maybe I then just skip a little bit and just show you maybe an outlook. So what you now saw was somehow that we have an inner approximation of this non-negativity comb, which gave us somehow a hierarchy of lower bounds converging to the optimal value. We can do the same with upper bounds. So we somehow very abstractly on a new Zignomial moment theory came up with a theorem that leads to upper bounds. So we have outer approximations of this cone of non-negativity, of non-negative Zignomials, and this yields us hierarchy of upper bounds converging to the optimal value. So this also comes with a dual formulation. Yeah, and there is a small issue here which comes from the measures, but I spare you with that. Yeah, so maybe let me just quickly go over this take-home message. So what you should take away from this talk is that we introduced this new Positivstellensatz that respects really the structure of this new concept of Zignomial rings we introduced, and it's the most general Signomial Positivstellensatz to date. From that, we derived a canonical hierarchy based on this A degree of the Signomial, and also demonstrated the hierarchy's practicality. So you just saw that it's rather competitive with these nonlinear programming solvers on hard Signomial programs. And we also ran other examples which could be also tackled via polynomial optimization solvers. And here we have the takeaway that it's much faster than this moment-SOS methods, one has to say for high degree sparse polynomial optimization problems, because there's where the strength of this new method really is. Yeah, and 4 and 5 I skipped a little bit here. So, and yeah, open questions here are clearly we would like to know how to somehow choose the best Signomial ring, because there are really differences in the complexity. So we would like to somehow study how one could a priori know which ring to take. And yeah, there are also tons of open questions regarding somehow this Zignomial moment theory we introduced and this upper bounds hierarchy. But with that, I think I finish. Thank you.
Thank you, Mareike, for your nice talk. Now is the time for discussions. Anyone in audience, if you have any question or comment, please unmute yourself and ask a question to Mareike. Please.
This solution recovery that you mentioned in the end, how does that work?
Yeah, that works actually. So maybe give you only a glimpse of how it works. So where is the dual? So it works with the dual formulation. So where did I have the dual formulation? That's why I popped up this slide with the dual formulation here. Yeah, so you can, so you have here this auxiliary variable z, right? And so this facilitates somehow the solution recovery because you can somehow invoke this how to say, this variable to test if this solution you have is feasible or not. So and this gives you, so to say, an entry point with a slightly additional stuff that gives you basically this solution back.
Yeah, but let's say, I mean, what you do is you construct these bounds one by one, and then you say, I'm satisfied because my function value, oh yeah, actually, what I have a bound, and so let's say your bound is 50, and how do I, from this bound, how do I get then the z? I mean, or how do I get the point at which this bound is satisfied? Or this bound is almost attained. I don't see, I mean, this is like a bit like cutting planes, what you're describing now, right?
Yes. Yeah.
And so what operation gives me then the x? I mean, where does the x come from? This z is the Z like the cutting plane?
Yes, basically. So by you can also use like branching and bounding to then recover this this set.
Yeah. Okay.
Yeah.
Okay. Thanks, Janus. Any other question or comment? Maybe I have a quick questions. I see that you have very nice application on polynomial optimization, right? But in your example, it's lower degree, and it low degree, and in the conclusion, you said that your method is faster than SOS for higher degree, right? Do you have any example for higher degree?
I'm not sure if I understood that right. So
yes.
The problem itself has to be of high degree, or not has to be of high degree. So when the problem is of high degree, then usually this SAGE approach works better, because as you know, this moment-SOS approach works with semi-definite programs, right?
Yes.
And they are usually in have complexity n plus d choose d. So n is the number of variables and d is the number, the degree. So it grows exponentially, right? And there is only so much we can do even nowadays with good solvers. So and for relative entropy programs, which are used here, I already said that this is not degree dependent.
Okay.
Yeah, so we can bump up the degree, and it does not really affect. It does affect, but not in this amount, like
okay,
this exponential amount, right? As for this semi-definite programming.
Okay, that's good. Thank you.
Yeah, and thank you for this nice question.
Yeah. Okay. Any other question or comment? So if not, let's thanks Mareike again, and thank you for your nice talk, and
thank you.
Thank you everyone for joining today, and hope to see you again.
All right. See you. Bye bye.
Bye bye.
Bye bye for now.